Right, and this is our second story, which is this is an NSF, National Science Foundation, and DOE, Department of Energy collaboration for the Vera C. Rubin Observatory. So the sort of headline on the nsf.gov website is, beginning in 2025, NSF DOE Rubin Observatory will embark on the Legacy Survey of Space and Time, a 10-year survey of the night sky using the biggest camera ever made, capturing an ultra-wide, ultra-high definition time-lapse record of the universe.
Yeah.
Which sounds incredible. And so help me understand the importance of this new observatory and what it actually is.
You know that previous story we were talking about?
Yes.
With 3i Atlas?
Yes.
If Vera C. Rubin Observatory had gone online a month before it did,
yes.
It went online in July. If it went online in June, it would have found this object within 3 days.
That's incredible.
Okay, that's what this observatory is doing. This observatory is American exceptionalism at its finest.
Hoorah!
It really is. Nice shirt.
Yeah, oh,
nice jersey.
Good. You see these 4 stars?
Yeah.
That means we're winners.
How do we get 4? Wait.
The women's team.
Okay, got it. Okay. All right. Well, hey,
we'll take what we can get.
We'll take what we can get. Yeah, this observatory is, it's like one of the greatest observatories that mankind has ever built.
Okay.
It is very different from other observatories. Very, very different in that traditional observatories, the whole point of the observatory is like the way it works is you're an astronomer. Mm-hmm. You got some idea for a bit of research that you want to do. So you write to the observatory funders or like whoever's in charge of like allocating time. And you say, this is what I want to look at. This is how many nights it's going to take. This is why it's important for science research, blah, blah, blah. And then they get a bunch of proposals. And then they allocate the yearly time budget to whatever you want to see. This observatory has no such thing. Okay. There's astronomers can't bid for time. And yet astronomers are super excited about it. Okay. This observatory's only job is to take a picture of the night sky, the entire night sky, every 3 nights. Mm-hmm. And that's it. That's it. Like robotic clockwork. Mm-hmm. Okay. It's almost like just a robotic telescope.
Yes.
It takes a picture of the entire night sky.
Yes.
Every 3 nights. Mm-hmm. Now that is impossible with other telescopes. This thing had to be engineered specifically for that task.
It seems like a brilliant use of time and money because it creates this baseline data set that's very robust, that creates a treasure map effectively for people to then say, okay, if I look at what's going to come out of the Rubin Observatory, you can get a baseline reference point and say, hey, this looks interesting over here.
Yeah. And
then we can zoom in with other tools that are maybe more specialized for any number of different types of observations.
Yeah. It's not just a baseline. It's like, it's actually going to find new things actively.
Out of the box.
Actively.
So people can just look at it and be like, oh, that's new.
Yeah. And in fact, I mean, it's going to have so much data that like people can't afford to look at it.
Right.
There's just too much data. They're actually going to have artificial intelligence looking through and combing through the data. Okay, so let's get into it because there's so much. This thing started 15 to 20 years ago. Okay. There's these things called decadal surveys in astrophysics. Mm-hmm. Okay. So, I mean, people might think that like scientists are just like, they just have like ideas and then the government's like, oh, okay, here's like $400 million. Right? That's not how it works.
Right.
A bunch of scientists have to come together because this is a lot of money. Observatories are incredibly expensive, right? Every little thing you're doing is at the cutting edge of science and technology. You're making the biggest camera. You're making the biggest lens. You're making the largest system for like distributing data and like finding stuff in data, right? All of this stuff is at the cutting edge, right? It's going to employ like hundreds and hundreds of researchers, right? Sometimes thousands. So in order to justify this kind of spending, there has to be a consensus in the community to actually say, look, this is the total budget the NSF and the government is giving us. How are we going to make use of it with big projects, because this stuff is big.
Mhm.
Okay, this is hundreds of millions of dollars.
And I want to make the note that
I don't know if it's hundreds. I don't know how many million this is actually.
this is also work that the private sector won't do.
No, why
And
would they?
Because there's no clear profit,
Yeah.
immediate profit value to investing that amount of capex.
No,
Eh.
this particular one was really nice because, Congress has a mandate that I think by 2030, they want to catalog all, like 90% of all near Earth objects that are bigger than 140 kilometers.
Mhm.
Okay. They want to just get a catalog of them all.
Mhm.
And NASA was like, all right, well, if you want that, we're going to need money to make an observatory exactly like this. This thing is going to catalog something like 65% of it.
Okay.
Okay. And what was funny about this particular project is in 2018, Congress actually gave them more money than they asked for because they wanted it done faster.
Yeah.
But at that point, they weren't limited by money.
Right.
They were just like, no, we got the best people here.
Yeah.
There's not anyone else who can do what we're trying to do. Like making a 32 gigapixel camera takes time. Grinding this lens takes time. Like you this is not a throw money at the problem kind of problem.
Right.
This is now we have the money, but it requires time to get this right so that like when we see first light with this telescope, it's going to be banger. And it's so funny because this is the one time Congress was like, at 4 scientists, they were like, you know what? Yeah, here, have more. And it's the one time that we were like, I wish you. There's so many other.
I think what's interesting about this is this idea, how times change, right? It's not a guarantee that the funding pool will always be there.
And this is 2018, so this is during the first Trump administration.
Right.
So it's not like,
right.
It's not a party type thing. It's just sometimes we really like science, and then all of a sudden, I don't know, something happens.
COVID in this case. I will note that on the nsf.gov website, they mentioned the amount of data gathered by the Rubin Observatory in its first year alone will be greater than the data collected by all other optical observatories combined.
Yeah.
Which is a massive amount of data. It goes on to say countless discoveries in improving our understanding of the nature of dark matter, dark energy, and other long-standing cosmic mysteries.
Yeah. It's got 4 mandates. Okay. The first thing is first actually let's get into what this thing is doing. Okay. So this Vera Rubin telescope, it's an 8-meter telescope.
Okay.
It's not like the Keck or the James Webb where it's a bunch of segmented mirrors. This is a single solid mirror.
Wow.
On the bottom. Okay.
Okay.
It was made in the University of Arizona.
Okay.
The University of Arizona, there's a lab there that is the world's best at making single big mirrors. Okay. And so when time came to make this, it's like, okay, we all know University of Arizona is going to do that. That's your job. You do it. Okay. They made this massive mirror. This mirror is extremely wide, right? 8 meters, but it's also like the field of view of the camera, the way the mirror is shaped means that the field of view is extremely large. Okay. What does that mean? That means so most telescopes, when they look at the night sky, they're looking at a patch of the sky that's smaller than the full moon.
They're looking at a very narrow.
Very you hold your thumb out and it's like that big. Yep. And they're looking like that. Okay. So even sometimes smaller. Same thing with James Webb, the Keck telescope in Hawaii, Hubble, same thing. This thing is going to look at a spot in the sky that's like 45 full moons.
Oh, wow.
At the same time. It's
several
like a palm.
orders of magnitude.
Yeah, it's almost like a palm.
Okay.
As big as a palm. Right? It's 1,000 times the field of view of Hubble. Okay? Now, if I want to look at something really close for a really long time, this isn't the thing to do it. But if I want to see the whole night sky in 3 nights, this is the thing to do it. What this thing is going to do is 30 seconds, then it'll take 5 seconds to move, 30 seconds, then it'll take 5 seconds to move, 30 seconds, 5 seconds to move, 30 seconds, and it'll map out the entire night sky every 3 nights.
So it's
in all of the filters.
It's making almost this giant, panorama is not the right word, but this giant mosaic of these 30-second snapshots that ultimately will create this sort of 3D.
Yeah, it'll be
map.
like the Vegas sphere.
Yeah.
But like every night.
Every night.
Okay. It's 60 petabytes of data over 10 years.
I was literally going to say, I don't envy the data.
60,000 terabytes of data. Like every night it's gonna be making like incredible discoveries because it's observing the whole night sky.
Which is something we've never done in this way before.
Yeah. And each of these pictures is going to be 32 gigapixels, right? So that's 32,000 megapixels in my palm, right? That I'm like with a giant 8-meter aperture. Right. The camera was built by SLAC.
Mm-hmm. Oh, really?
Stanford Linear Accelerator Lab.
Different SLAC.
Yeah. Not the
workspace management software company.
Yeah, again, the private sector isn't going to do this, right? But the government and SLAC is part of the DOE. So SLAC made this camera. The camera is like going to fit in this room. Okay, it's like as tall as you or I.
Okay,
and it's like as wide. You can imagine, like it's the world's largest camera.
Yes,
32 gigapixels.
Yes,
right. I mean, in 30 seconds, we want an exposure on this small patch of the sky. It's incredibly detailed, dude. You see like galaxies you've never seen before. In the first 2 days, it discovered like thousands of galaxies. Right? In the first 2 days, it discovered 2,000 asteroids that we've never known existed.
That's incredible.
And it's like, wait. Like,
yeah, right.
Those are asteroids. Like that could be bad.
Right.
In the first 2 days, 2,000 asteroids that we should definitely know about, and we don't. There's 1 million known asteroids right now.
Okay.
This thing is forecasted to get 5 million more in the next 10 years. So over the past 200 years, we've observed 1 million.
Right.
And now in the next 10, we're going to observe 5 million because of this thing. Because all it's doing is taking a picture of the entire night sky every night.
Yes.
And then it's going to look for, it'll be super obvious.
Right.
When an asteroid moves, right? When a small point of light moves, we can literally track it over the whole year.
This seems like a perfect use case for, AI detection and anomaly detection algorithms, because we have a decent amount of data to create sort of structured algorithms as a starting point that will identify things like asteroids, et cetera, and then we'll put them in these buckets.
And AI is really good at that kind of stuff, right? Anomaly detection is like huge.
And so we'll have these buckets of stars, asteroids, galaxies, and then there'll be this fun other bucket where it'll just see new. I mean, it's like putting on glasses when you're like really blind, or turning on the lights further down into a room where it's like we've seen some stuff, but we've not really seen it all.
Mm-hmm.
And it is going to be an incredible amount of the fidelity to me is what's crazy.
And the clarity of the images and the amount of light gathering power that we have here is going to be insane. Like the first thing that, like, there have been surveys in the past.
Sure.
Right? Like Harvard has like the Harvard Plate Archive, which is like back when there were photographic plates.
Yes.
Palomar has one, Mount Palomar.
Yes.
You know about that one.
Yes.
And then the most famous one before this was the Sloan Digital Sky Survey. That was in New Mexico. And back then, like, there's internet, but for this amount of data, there isn't. And so like dudes literally had to like fill up luggage with like the data and then bring it to the university, like physically. Right. Now this thing takes a photo, within a few seconds it's to California, to France.
Mm-hmm.
And then within another few seconds it's going to be checked across every other photo that we've taken of that spot in the sky, because the telescope's tracking where it looked.
Mm-hmm.
Right. And then maybe Hubble looked there, maybe VLT looked there, like 5 years ago or 10 years ago. You check around there, and then if there's anything different, it's going to flag and go across to all the astronomers everywhere being like, hey, there's something cool here.
I want to be on that email
and so like
thread.
every like minute that it's observing, we're going to be seeing these things. And the cool thing about this is there's no embargo on the data. Okay, you know how I was saying about like the James Webb Telescope?
Yes.
3 months,
Yeah,
right?
yeah.
You get 3 months to massage your data, get your paper out. Here, it's like it's out.
So
It's out like that night.
it's not only a new technical innovation in and of itself, it's a first of its kind observatory, but also the workflow that is accompanying the observatory in terms of data access to a wide community of
Yeah.
scientists is also fundamentally different.
It's fundamentally different, and it's like it took like the software, the kind of software that was required to do this,
Right.
and the kind of electrical experience and all of that stuff that could only happen in America. Like the amount of cloud computing that is happening because of this thing is like something that it's actually being handled by Fermilab and the University of Illinois, because like particle detectors, they have experience with like ridiculous amounts of data and how to make sense of it.
Yep.
Right? This is a great problem that now they can solve. So the University of Illinois is actually in charge of this whole data pipeline that's happening, and they're still massaging it out right now. Like the telescope is live,
Right.
but like this is a part of the pipeline that they couldn't really test
Right.
until they started getting the photos.
It's
right?
Still, it's still in beta.
Yeah, like so everyone was focused on, okay, let's just get the photos.
Right.
Now it's like, okay, how do we get the photos to everyone?
Right.
And it's slowly coming about. Now, I said something about how there's no embargo on this data. So the telescope takes a photo tonight, it's out. Now we have public access to this data through the Vera Rubin website. There's actually like citizen science efforts going on because, as you said, right, machine learning is going to be really, really powerful for detecting anomalies and detecting new objects in this data. But what does machine learning need? Training data.
Yeah, training data sets.
Training data.
Yeah.
And so how's the like all of the training data, like the LLMs, the training data is coming from humans writing on Reddit and all this other crap, right?
The internet, right?
The internet,
the text of
right.
The internet.
So like there's all this text on the internet, that's your training data. But that text fundamentally had to come from human beings for it to learn how to speak like a human being and like language and logic and all that other stuff.
Right.
This, we're gonna have citizen scientists doing training annotations on the data. So already something like 100,000 images. It's only been like less than a month.
Yeah.
But already 100,000 images have been looked at and labeled for comets.
Yep.
Okay, because comets look a little bit different from asteroids.
Okay.
So there's a bunch of people on there, and you guys can like go and like be a part of this effort.
Right.
Like you basically identify, is it an asteroid, which is just a point-like thing that is moving, or does it have a little bit of fuzz around it?
Right.
Okay. And that's your job.
We need
Is
more
just like-
reinforcement learning from humans.
Yeah.
And so I actually didn't know that. That's fascinating.
Yeah. So these guys are this is just classic data annotation.
Yep.
And then we can then train the machine learning algorithm and the AI for the future.
Yes.
And then we won't need we can have them like do other stuff.
Yes.
Like, okay, is this a spiral galaxy or an elliptical galaxy? All sorts of stuff.
This is, I think, one of the things that's so fascinating about that part of the story is that it is this reminder we always talk about, which is that science is for everybody, right? And it should be accessible for everybody. So it's actually really heartening to hear that.
Yeah, this one, I really like that. That like, they got all this funding from the American taxpayer, but they're giving it back.
Right.
Not just to the American taxpayer, but to the world.
Right.
It's kind of cool.
I
think it should make us very proud as Americans that we are still at the forefront of astronomy.
Yes.
Ever since the 1920s.
Yes.
Like we built the biggest telescope in the 1920s, and we haven't stopped.
One thing, the biggest, the best.
Yeah, that I think we really do understand that adjective, biggest. It's like, okay,
bigly.
yeah, we're gonna make the biggest. Although we didn't understand that when we tried to build a superconducting super collider in Texas. We almost built it, and then
CERN,
and then we ran out of funding during the Clinton administration
when we had the crazy budget surplus.
Yeah,
interesting.
Like Reagan actually like gave money for it. But that okay, fine. That was during the Cold War, so maybe one can. But basically, once the Cold War ended, even the Democrats were like, "Oh, I guess we don't need science anymore." It's so annoying. It's unbelievable. Like now, there's just a giant tunnel underground in Texas. There's a giant tunnel with graffiti and stuff.
Don't tell
Elon.
Because
we bored a tunnel, but we just didn't put the detectors in because like we ran out of money. It would have been bigger than CERN. You understand?
Really?
Yeah, it would have. Dude, we would have found the Higgs like 20 years ago or something.
This is why we need to fund.
It's incredible,
science.
and like it would have been a larger search space. Like we would have answered questions about supersymmetry, the fact that it doesn't isn't there in these. Like we would have answered all that because the luminosity for that Texas superconducting supercollider was higher than CERN's is right now.
Which when it's been ramped
Like
up.
when we do stuff, we plan to like it was gonna be bright and it was gonna be big.
Big.
And then money ran out and then we didn't give the money. And then that's when I think we learned our lesson, and that's when NSF was like, no, we're going to do, with whatever limited budget we have, we're going to take big risks and get big rewards. And that's when LIGO sort of got in the mix. And that's when people started asking, okay, can we make this gravitational observatory?
Right, well, this is the gravitational
wave observatory.
Yes.
And finally LIGO got funding. Like, I think it was sort of a backlash from like that failure that we had as American scientists.
Right.
Yeah, we were just like, we really dropped. And like now, at CERN, we're kind of like second-class citizens because to be like part of the fold, you have to contribute something like 1% of your GDP, which is fine for something like the Netherlands. But like the U.S. is all of Europe plus more. It's like you want 1% of our GDP. No, But it's like, but they need our magnets. Like CERN couldn't work without our magnets, and like a lot of the tech and a lot of the like big electronics was coming from America. So yeah, I think that we didn't really like that. And then like we made LIGO. I love that in astronomy we're still like at the forefront. We're making James Webb.
Yep.
We made Vera Rubin.
Yep.
The Keck telescopes in Hawaii. Like we're still going at it. There's a new one that's like planned. It's called the Nancy Grace Roman telescope. That's going to be in space. It's going to be very similar to the Vera Rubin telescope because it's going to have a really big field of view. But unfortunately, I think that one has been put on pause because it hasn't been launched yet.
Right, and the
funding is stopped. So that's something that like we clearly should like really like invest in. Yeah. Oh, you're looking at the photos.
Yeah, I want people to understand, and we'll put
look at like all of those dots. Like all of those dots are previously unknown galaxies.
It is incredible, and it's what you can see.
That's a single that's a single night,
and it's basically this map view, with part of it filled in from where the photos have been taken, and it's just going to continue to expand over time.
Yeah,
and you can just zoom in, and it's pixelated for a little bit. And then it gets high fidelity, and you just keep zooming in.
And then finally you get to the signal to noise of the detector.
Right.
Yeah.
But, I mean, there is an incredible amount. There are incredible amount of objects in this view.
Yeah, like you see some of these like diffuse galaxies here?
Yes.
Those like were so diffuse that they weren't even caught in the Sloan Digital Sky Survey.
This is incredible.
Right? But that's like some of those are totally new galaxies that are pretty close to us.
And we just didn't even
we didn't even see because like they were just sort of like blobs of particulate stars with no real structure, so they weren't bright enough. But now this thing is incredible. And the thing is, it's going to take pictures of the same spot in the sky, right?
Right.
At the end of the day, it's over 10 years.
Right.
You can start not even looking at the movie aspect of this, right? Like the time-lapse aspect of it. You can start averaging the same spot.
Yep.
Right? And then get insane signal to noise.
Right. Right.
And then start seeing really faint stuff.
Yep.
Right?
Yep.
And so, and this is, it's only been a month. And already we have like thousands of new asteroids, thousands of new galaxies.
This is incredible. I mean, this imagery is unbelievable.
It's unbelievable. And the amount that we're getting,
right.
The sheer amount, like, it's doing a whole night sky. And then the other thing we got to remember is like, let's say the sun is here.
Yeah.
Let's say the sun is here and the Earth is over here.
Yeah.
Okay, it's in the southern hemisphere.
Yes.
So it's only going to be able to see like this part of the sky in one night, right?
Yep.
And then as the Earth rotates, it's going to basically see all of this down here.
Mm-hmm.
So there's going to be parts like near the equator that we're going to have like a movie for like, we're going to have all the photos for 5 months, and then we're not because it's going to be on the wrong side. And then it'll be back. So then like, we'll see like, but then there's parts near the South Pole that are just always going to be visible. So we'll just have like a 10-year full-on movie time-lapse
of the universe,
of like the universe in this like down here,
right?
Because it'll always be nighttime down there,
right.
And so that'll be really cool.
That's gonna be, I mean, the image, like, even already,
It's gonna be so awesome, dude.
This is incredible. I want to end this story with this little bio snippet that the NSF put out on who was Vera Rubin.
Yeah.
The Rubin Observatory is named in honor of Vera Rubin, a pioneering American astronomer whose observations provided convincing evidence of dark matter, an invisible substance that makes up over 80% of all the matter in the universe. Rubin's work in the 1970s showed that galaxies were rotating too fast to be held together by visible matter alone, suggesting the presence of an unseen mass.
Yeah.
Her discovery reshaped our understanding of the universe. Dark matter is unlike any known type of matter, and its true nature remains one of the greatest mysteries in science today, inspiring generations of researchers and science lovers, and one of the greatest observatories that humanity has ever created to date. And so in honor of Vera Rubin, a woman in science.
Yeah, she was snubbed for the Nobel Prize.
Which is incredible.
She should have gotten the Nobel Prize. It's an incredible discovery. She did these, what they're referring to as galaxy rotation curves. Okay, it was the first sort of real inkling that, okay, there's something real wrong. Like, where is everything? Why can't we see it? Basically, it's a very simple observation, okay, that she was making, which is that, like, stars that are, like, farther away from the galaxy center should be moving slower, right? Jupiter moves way slower than Earth. Mercury moves really fast around the sun because the closer you are, the stronger the gravity, and so the stronger the acceleration, which means you're going to move faster. Okay, fine. What she noticed was the galaxy rotation curves, instead of doing this, instead of trailing off as you go farther out, they remained constant. So what does that mean? It means one of two things. Either Einstein is wrong, unlikely, or there's a bunch of mass there that is contributing to this gravitational pull that we're not seeing.
Right.
Okay?
Right.
And that's where sort of the dark matter debate started.
Got it.
It's like, is it dark matter or is Einstein wrong? The Vera Rubin Observatory, which is named after her, one of the key, like, pillars of its creation is this idea of answering that question. Okay? It's like, I mean, you saw those photos, right?
Yes.
Galaxies upon galaxies of stuff. What it's going to be able to do is map out the entire universe from extremely large distances.
Yes.
And what we're looking for is structure, large-scale structure. What that means is, like, so it turns out the universe is not, like, completely isotropic, in that it's not completely the same everywhere.
Right.
There's clumps of stuff, there's clumps of galaxies, and then there's giant voids that are, like, millions of galaxies big where there's nothing. Okay, not you know what I mean, low density, high density.
Yes.
And so if we can map out that structure of, like, where the high density is, that's where the dark matter is, and then where the low density is, then we can start figuring out how much dark matter there is, and how that dark matter evolved from the beginning of evolution. We can start making not evolution, from the beginning of the Big Bang, from the evolution of the universe, from the Big Bang until now, like, how that dark matter evolved, how it shaped the creation of this large structure, and all this other kind of stuff, right? That's one of the things it's doing. The other thing it's doing is, because it's, like, just going through galaxy after galaxy, it's going to catch a lot of gravitational lensing, right? It's going to catch these, like, instances where the light is bending because of the mass in front of it. And then once we have that, we can have a better estimate on how much mass there is to bend that light. And then we can start discovering things about dark matter. The more data that we get, the more closely we can start scrutinizing stuff like Einstein's general relativity, which we sort of take for granted. But, we'd need something like thousands of galaxies. I think it might honestly be, somebody did the calculation, it's like on the order of millions of galaxies worth of data to really start honing in on this question. And Vera Rubin,
it's going to give us
given that it's doing this, it's going to be able to do that.
Yeah,
it's going to be awesome.
Unbelievable. We're gonna come back to this.
Oh yeah, this thing is gonna be in our zeitgeist for the next 10 years.
Right.
It's gonna be finding crazy stuff, like it's gonna be insane. Like IceCube and LIGO. We've talked about IceCube and LIGO on this podcast before. The only time, like, Vera Rubin it's on a mandate, right? It's doing this. That's it. It's not gonna. You got something nice to see? Go look somewhere else. Except for when IceCube or LIGO
Detects.
see something crazy.
Mm-hmm.
Okay? If they see something crazy and IceCube is like, yo, there was a massive neutrino that just came out of there.
Yeah.
Then Vera Rubin's going to be like, all right, I'll take a break, point it there. And because of Vera Rubin's like big field of view, because like when stuff comes into IceCube, we kind of generally know the direction it came from.
Mm-hmm.
But it's not like other things where it's like, oh, you got to go to that star, look a little bit left, look a little bit down, you're good to go. No, so Vera Rubin's got this giant field of view. It can just point and like start perusing that patch of the sky,
right.
waiting for the signal.
It doesn't have
right?
to be super specific. It can have a general region of the sky to look at, and because it's so high fidelity, it's going to just get everything. Both where those neutrinos are coming from, and
it might see like, and it'll have, so the neutrino probably came from like a massive supernova or like some giant, quasar bursting or something like that. This thing can look, and it'll have the image from the previous nights.
Right.
So it'll just compare immediately, be like, oh, that's different.
Right. Ah, yeah.
Yeah, and then it could tell all the other observatories, yo, look over there.
Yep. Because it'll actually get the core, like it'll have basically the direction of like, oh yeah, we have all this historical data from the Rubin Observatory. IceCube told us to look, something is different, and the different thing is right there.
Yeah. Like if neutron stars create gravitational waves, LIGO's going to find out.
Mm-hmm.
LIGO and Kagra and Virgo, but their resolution is also based on like whether the gravitational wave hit this thing first before this thing, right? Their only resolution of direction is like the timing difference
between the two. Yeah.
And so they're just like, it's in this general direction. Vera Rubin can go and be like, okay, let's find it. Like this is it's a long time coming. That's what I was saying. Like in the Decadal survey, like 15 years ago, the astronomers came together and were like, we need something like a large survey telescope, whose only job is to survey the night sky, because we're tired of living in still pictures. We want to upgrade to movies now. And so we need one telescope that does exactly that.
That's actually a great analogy. We're moving from photography to videography in space. It's a loose analogy, but
no. I mean, and so actually it was called the large synoptic survey telescope. Lame. And then they renamed the observatory Vera Rubin Observatory, and then the program now, they kept the LSST, and they called it now the Legacy Survey of Space and Time, which is sick.
That is, I love that. Shout out to the acronym creators.
Yeah. They love their acronym so much they kept it, but they just like upgraded like what it stood for. It's a great story. I mean, I'm so glad this thing is up. You can go see it. It's up and running.
Yeah, like you can go right now to nsf.gov and look at the Rubin Observatory page and literally see the field of view explorer of right now. They have their first images on there from January 23rd. One day, like I can't. You guys have to go look at this. The amount of stuff that it captured in one day is crazy,
and it's the first time the humans have ever seen that.
It's crazy.
That stuff. A lot of that stuff, right? There's also another spot, I don't know if you can find it, but like there's an asteroid like explorer where they map out like all the asteroids that Vera Rubin has seen.
That's incredible.
And so you can just go look. I mean, it's really awesome. Like these are your taxpayer dollars at work.
You know what'll be
it's an incredible gift.
It is. I can't wait for there's this video game, I think it's called Star Citizen. That is a procedurally generated universe, but it's like highly,
Oh, dude, I think I've heard about this.
It's like it's super high fidelity, and like you travel at real space time, like real. It's equivalent to like the actual traveling distances and stuff like that, modified a little bit. But what I would love to eventually see is someone take this and then replicate a explorable 3D environment. With this as the backing data that powers
because now we'll have 5 million asteroids. Right.
And they'll be cool to sort of
and they'll be like real.
Right.
With names and shit.
Oh God, I want to name one. Let's name one the Krishna Lester asteroid.
Yeah, the first principles asteroid.
The first
FPPA.
An amazing story about the brilliance again. A little American exceptionalism in there. We'll give the old badge a nice kiss.
No, we deserve it. That's dope.
This was a good one.
Yeah.
This was a good one.